notes today. I need to be pretty much as soon as I'm done with the webcam class. Tomorrow I'll be all day in my office. I have a meeting from 3 to 4. Other than that, you can have much anytime. So, we left off last time talking about adding to a carbonyl either hydride ion, a reducing agent, or a Grignard type thing, and the difference between adding once and adding twice if you're starting off from an acid chloride or an ester, particularly an acid chloride, which is going to be active than an ester. So, starting from an acid chloride, lithium aluminum hydride you're going to add twice, go to the alcohol with very large groups, TB toxic group at low temperatures, you're only going to add once, go to the aldehyde. Grignard, you're going to add twice, large organocuprate, low temperature, you're going to add once. So that's what's going to allow you to do aldehydes or ketones in this chapter, which is about aldehydes and ketones, as opposed to in chapter 10, when we're looking at ways of making alcohols. Well, that was a way of making alcohols. All right, so moving on. This we haven't seen before. So, talking about organolithiums, when we talk about Grignards, if we're talking about a Grignard, the way that you make a Grignard is you take some sort of a halide, whatever it is, you put magnesium, you form the Grignard, and you make this carbon nucleophilic. Well, we can also put an excess of lithium and again, this is not that simple. It's an organolithium, blah, blah, blah. But this is kind of sort of like a Grignard, except this is more reactive than a Grignard, but both give you a nucleophilic carbon. And it is both a very strong nucleophile, but of course it's also a strong base, just like Grignards are. We don't use it that much because they are very reactive. And so usually, you don't want things that are way too reactive if you can get away with something a little bit less reactive. But this is an example where we're going to have a carboxylic acid. And it's going to be, this thing is going to be acting both as a base and a nucleophile. So if you have a carboxylic acid, and you come at it with an organolithium, if you have something whatever this is, that could attack here or here, which one do you think is going to be easier? Your acid-base reaction, if there's competition between acid-base and nucleophilic, electrophilic, the acid-base is always going to win. That hydrogen is always hanging up there, easily exposed, easily available, while making its way here between these groups is not nearly as simple. So if you only had one equivalent of your organolithium, it's going to go for the acid and you're going to form the salt of the acid, right? So if you put one equivalent of your organolithium, let's say you had, I don't know, this, where did I get this organolithium here? If I write this, that means this is your negative charge, now on the benzene ring. And of course, that came from, just like with Grignards, from bromobenzene. So from bromobenzene, add magnesium from a Grignard, from bromobenzene, add lithium, form the organolithium. Okay, same deal. First thing this is going to do is your acid-base reaction and form this carboxylate ion, this lithium salt. Okay? That kills off this because now you have benzene. But if I put a second equivalent of my organolithium, now there are no more acidic hydrogens, so now my second equivalent is going to act as a nucleophile. And so you're going to form this carboxylate ion and have this over here. Until I do something different, this has nowhere to go. So it's going to stay like that. Now, this is a powerful base. You're not going to put this in water. It's a powerful base, it's going to react with water and we just kill the base. Okay? Things like N-butyllithium, you know, this organolithium, not a trace of water. Super dry solvents that have no acidic hydrogens, or you just kill this very expensive thing because it's not easy to make and you charge you lot for it. Okay. So, not a trace of water until we get to this point. And if you toss now the whole thing in water, this whole thing is going to collapse. We can write different mechanisms. So this is a hydrogen and another one, and this collapses and kicks out this leaving group. But at the end of the day, we're going to get rid of water and we're going to form a ketone. Now, why is this important? If I had started from, let's say, an ester, and I added my organolithium or Grignard, whatever it happens to be, what would have happened? I would add once, I would add twice, and I would form the alcohol, right? After I hydrolyze. But this is in essence a way to stop at the ketone, not add a second time. And the reason is, I'm still using an excess of this, right? I'm using 2 equivalents of this. Same as in here, we'll be using 2 equivalents of this. But in here, my first equivalent, adding to an acid, not an ester, is the acid base. And once I convert it into this is not a leaving group under any possible scenario until I hydrolyze it. And so it's going to stay like this and allow for the second equivalent of my nucleophile to add and remain stationary like this without being able to kick this out, without being able to add again, until I toss a whole thing into water. And then it collapses and it gives me the ketone. So it's just another trick to not go all the way to the alcohol, but to start with the ketone. Okay? But you must start from a carboxylic acid, which is different from what we've done before. So that's that. From carboxylic acids using organolithiums, you're going to put two equivalents of the organolithium. The first one as acting as a base, the second one as a nucleophile, form this intermediate that is not going to do anything until you hydrolyze. And then you're going to form a good leaving group. This is going to kick it out, and you're going to be left with a ketone. Okay? So yet another way of making ketones is done from carboxylic acids. Okay. Ketones from nitrogen. So we talked about nitriles before. Nitriles are obviously polar. Like a ketone, like a carbonyl, carbon bond oxygen, a Grignard could attack them, right? When you talk about a ketone or aldehyde or whatever, and a Grignard comes, you form this alkoxide ion, this and this stays like this until you hydrolyze. Right? Well, if you have a nitrile, then same deal, your Grignard is going to come and attack, except in here you broke one pi bond, and here, right, and let's say these electrons are now here, in here you're breaking one pi bond, and your electrons are now here, and this is going to become a negative, and right, you're going to form this intermediate. And so we would be at this point adding one equivalent of my Grignard. Now, something is going to need to happen when I toss this in water. Okay? But the key once again is this cannot react any further until I toss this in water. So a carbon double bond nitrogen, like we have in here, this is called an imine. So we form this imine intermediate that cannot react any further until we toss it in water. Now, once we toss it in water, let's remember, the whole trick is to stop something so a second equivalent doesn't add up and you end up with an alcohol. These are all different tricks to stop and end up at the ketone or aldehyde rather than going on to the alcohol. So what happens in here when you toss it in water, this picks up a hydrogen, acidic water, we're going to pick up another hydrogen, water is going to attack, we're going to form a sort of intermediate like this. After we lose a hydrogen, this is still acidic, my nitrogen is basic, this is going to pick up another hydrogen, and become a good leaving group, and my oxygen is going to kick in, kick this out, eventually we're going to lose that hydrogen, and here is my ketone. E means hydrolyzed to ketones, reasonably easily. And so that is a way to stop right here, avoid a second equivalent of Grignard from adding, but then once I toss it in acidic water, but this is where we stop the reaction. But once we add it to acidic water, the imine hydrolyzes to a ketone, and then I avoided adding a second time. We're going to see variations of this quite a bit, imines hydrolyzing to ketones to whatever. Okay, so we saw ketones from carboxylic acids, using organolithiums, from nitriles, using a Grignard, right? Those are new kind of techniques that we're developing. So let's look at problem 7. So in A, starting from bromobenzene, we are going to want to make this compound, and then from propionitrile, we're going to want to make heptanol, and from pentanoic acid, we're also going to make 3 heptanols. So show me approaches to make each of these. And we can make all kinds of variations on this. Maybe we'll show a few variations, but try to come up with at least one way of making this. Let's do this analysis in the first one. What is, tell me ways that you know to make a carbon-carbon bond between a benzene ring and a carbonyl. Friedel-Crafts acylation would be one that really comes to mind. and of course the good old gradient. Now, what's my problem with my starting material if I want to use Friedel-Crafts isolation? Would I start from bromobenzene? No. No, you would start from benzene, and then you add that to an acid chloride. Now, I could potentially add lithium, form the organolithium, add it to water, that would get me benzene, but that would be kind of stupid. I have benzene in bottles all over the lab. But technically, I could do that and then do my Friedel-Crafts. But probably that's not what they're wanting me to do here. Okay. So, an alternative, I could make a Grignard from this and add it. But what would I want to add it to? If I add it to an acid chloride, I'm going to add twice and end up with the alcohol. How do I end up only adding once to form the ketone? Okay, first we have magnesium. We have a Grignard. Now, what do we do with the Grignard? Okay. I'm going to add it to the aldehyde, proteinate. That's going to give me the alcohol, right? And then I'm going to need to oxidize. But can I do this in one step? Some of the things we just looked at. So, Gilman reagent would be you starting with like an acid chloride or ester, acid chloride, because at those temperatures you really need something more reactive. And some organocuprate that has a couple of the things that you need. So let's say, potentially something like that, which would mean you need to make organolithium, then add some copper chloride, and then add that to this type of thing. So, okay, we could consider that. Make organolithium of this, then add some copper chloride to make something like that. Then add some acid chloride and eventually hydrolyze this at low temperatures and eventually okay. All right. What else do we see?
Organolithium to carboxylic acid.
Yeah. So rather than doing this rather complex set of things, we saw that we can add an organolithium to a carboxylic acid and stop it there, adding only once, and then once we're ready, we toss the whole thing in water and the whole thing collapses into a ketone. So this is going to be the organolithium. This is going to be my carboxylic acid. So, okay. So let's say I start with this carboxylic acid, and first, well, no, that's not what I thought I would do. I start with my benzene. I'm just writing this. So I'm going to make the organolithium. So add an excess of lithium to make the organolithium. Then I'm going to put my carboxylic acid. Allow for that intermediate with a salt lithium alkoxide to form, and toss the whole thing in water, and that's going to give me the ketone.
So all of these would be to get that ketone? Or
that's a good one. So there's all kinds of possibilities. Some are one step as opposed to two. Some work better than others. When you're doing research, you probably try all of them to see, because you're fighting you don't want to just get to the product. You want to get to the product in high yield, in as few steps as possible, sometimes with the right stereochemistry, whatever. So you try all your possibilities and then figure out which one works the best in the cheapest possible way. If you're in industry and you're making mega amounts of this, money is an issue. So if you have a cheap reagent versus an expensive one, you go for the cheaper one. That type of thing. Okay? All right. Let's look at the second one. So propionitrile to 3-heptanone. Okay, how do we do this? We just looked at nitrates, right? And if you add a Grignard to a nitrile, you form this imine that does not react any further until you collapse it with water and it gives you a ketone. So this piece is this piece. The Grignard that I'm going to want to add is this one, right? So what did I make this Grignard from? Bromobutane, you added some magnesium, that gave you the Grignard. You add this first, and then you toss the whole thing in water, and you're going to get your ketone. You need to figure out where your carbons are coming from. What bonds are you making? Is this a bond to a carbonyl, a bond to a carbon that has an OH? It's a different strategy. If you want to end up directly with a carbonyl here, that means you only add once to an acid fluoride or something like that, a nitrile, an alcohol, you might add twice or whatever. Okay. But analyze your starting material, your product, what bonds are you making, what strategies do you know to make a bond of that type. The third one was pentanoic acid to 3-heptanol. So same product, but now we're going to start from pentanoic acid. That's the bond that we're making. Right? And we just looked at carboxylic acid and said that if you have a carboxylic acid, add an organolithium to it, you end up forming a ketone. So to this carboxylic acid, we're going to add this organolithium, excess of course, because first we wanted to act as a base, make the lithium salt, and then as a nucleophile, where did this organolithium come? Well, that's the lithium you buy in bottles. Actually, you buy in cans, which are completely sealed cans, because you don't want any water to come in, and then you're going to perforate that can with a needle, and your whole syringe and needle are coming from an oven, completely dry, in a hood, in a nitrogen environment, because you don't want any trace of water, and you get that organolithium, and you inject it into your thing, which is also in a nitrogen atmosphere. You're trying to completely avoid any trace of even water vapor, and then you make the reaction happen. Once that intermediate forms, you toss them finding the boiling water, and it collapses into acidity. But if you were making this, you would make it from ethyl bromide or whatever, put an excess of lithium, and that was it. But you can purchase this commercial. So far, what we looked at is effectively this reaction. You had a carbonyl, often with, a chloride or a ester, but sometimes an aldehyde or a ketone, right? So whatever was in here. And then you came with a nucleophilic carbon, either in the form of a Grignard or an organolithium, and this added here. And depending on whether this was a good leading group or not, right, you had the alternative of if this was a good leading group, then this could come and kick this out and form some sort of a ketone. If this was not a good leading group, then once you toss this in water, you would end up with an alcohol, right? This is a nucleophilic addition to a carbonyl. And of course in here, then you could have a second round of this attacking and blah, blah. Okay. Now, what we're going to do is my nucleophile in here was either a Grignard or some sort of organolithium. We're going to look at another type of nucleophile called an ylid. Now, an ylid will be involved in what we call a Wittig reaction. So, first we're going to look at how do you form an ylid? This is effectively what an ylid is. Now, your ylid is formed kind of sort of the same way that you form a Grignard and the same way that you form an organolithium, and that is starting from an alpha K. So, I have this, I put magnesium, and I end up with a Grignard. I'll start with this, I pour an excess of lithium, and I end up with an organolithium. I add this, and I put triphenylphosphine, and this is has electrons, comes from the back in an SN2 reaction. This becomes positive, then I'm going to put a base, often something like N-butyllithium, powerful base. This is going to come, abstract this hydrogen, and put electrons here. And this is my ylid. Nucleophilic carbon, nucleophilic carbon, nucleophilic carbon. It is going to attack a carbonyl. You can see how people are thinking in similar terms, but what variation can I do here? Okay, now, what is going to be different here is we're going to add my ylid, as usual, to a carbonyl. Nucleophilic addition. This is, by the way, a true covalent bond, unlike the other ones, which were these metal complexes. This is going to attack. We're going to form the usual alkoxide ion. Okay, so this bond that we're forming here, let me show it right here. Okay, kind of make this over here. And okay, so we're going to have a carbon. We're going to have a carbon and a phosphorus and this. this carbon is CH2. So this piece is here, and this piece is here. And we just formed this new bond. What is different from this relative to what we studied before? Is that now we have an oxygen with a negative charge next to a phosphorus with a positive charge that are very willing to react together and form a covalent bond. Whereas before we were dealing with essentially ionic compounds, that was not an option. And then, because this is pretty unstable, this is going to kind of collapse. Think about these electrons are going to end up here, these electrons are going to end up here, and we're going to form a double bond here, and a double bond here. So, unlike previous examples where we made a carbon-carbon single bond, we've now made a carbon-carbon double bond, which is different. So this is a way of making alkenes. And you remember alkenes are super important. They're workhorses because there's 8 gazillion reactions that we can do from alkenes. Up to this point, what were the ways that we knew to make alkenes? I'll get to it, but let me finish this thought. Elimination. That was it, right? To make alkenes, these super important molecules that could be involved in a million different reactions, we would either eliminate, an alkyl halide, whatever type of alkyl halide, and we were dealing with major or minor elimination, so that became an issue. Or maybe an alcohol, a dehydration, but all of them were either E2 or E1 eliminations that would form alkenes. And again, in all of these, I needed to consider major versus minor, because of course, if this were, for example, this compound, then the alkenes that I would form potentially would be either this or this, right? So in certain cases, I would only end up with one, but in other cases, I could end up with a mixture. One would be the major, usually the more stable alkene than the substituted one versus the minor. But there were all those issues. Now, we have finally a different way of putting this together, which is unique because this half of my alkene is coming from the ketone, and this other half of my alkene is coming from the ylide. And then I put them together. I decide where my double bond is. It's not a question of it could eliminate from here or from here and I'm going to end up with a mixture. I have full control. What do I put here? What do I put here? Form the double bond. Okay? So that is a powerful way, right? You're starting from something like that. Well, let's make them different. And at the end of the day, whatever you do, you're going to end up forming a double bond here. And on this side, you're going to have this and this. And on this side, you're going to have that. And you decide how you're going to do that. Okay, so this is a new and powerful way of making alkenes. It's called a Wittig reaction. And a Wittig reaction involves ylids, which you make from alkyl halides with triphenylphosphine and a base. You form the ylid and add that to a ketone or aldehyde, and that gives you the double bond. Okay? Sorry, what was your question?
When you said that the bonds just collapse, what do you mean by that? To make the double bond?
Which bonds?
On the
Oh,
last
this-
step, you said they just collapse.
You kinda cannot stop this. So this forms, because they're right next to each other. But as soon as this forms, this is a four-membered ring with atoms that are very different in size. So phosphorus is humongous, the other ones are smaller. This is really uncomfortable, unwieldy, so okay, look. And then the whole thing breaks its bonds and goes to a much more stable situation. So this four-membered ring is only very temporary, does not really last long, and you don't need to do anything. It will just continue and break apart. Okay.
So if this was a question on the test, you would want us to show the mechanism. Like if you're asking for the mechanism.
Exactly.
You
So
want-
that's asking, show me the mechanism of how this forms from this. Then you will go through the four-membered ring. If I just say which is a product that forms, then I just want the product.
And you want us to know how the ylid is formed as well, right?
Yes, so again, let's keep in mind that all of these are very similar, where you're forming a Grignard, where you're forming an organolithium, or if you're forming an ylid. They all start from an alkyl halide. This is the way to make this nucleophilic carbon. It's just what those nucleophilic carbons then do given the rest of it. One important difference in here is the fact that this is an SN2 reaction. So if this were chiral carbon, then I would be, well, first of all, unlike Grignards or organolithiums, where I could start from this and form a Grignard or an organolithium, that's not an option with an ylid. It must be an alkyl halide. And not just any alkyl halide, but methyl, primary, perhaps a secondary, certainly not a tertiary. So that is different. You are so annoying. So there are some differences, some similarities, but try to see the similarities. They're all starting from halides, they all give the nucleophilic carbon, that nucleophilic carbon adds to a carbonyl, but then what happens from that point on is slightly different. Okay. needless to say, a Wittig reaction is the kind of Nobel Prize reaction that we make because really efficient way of making alkenes that are unsymmetrical and make them exactly the way I want to make them is a very powerful tool. Okay.
What's the reagent? I'm sorry. The reagent you added right before making the ylide?
Tritone phosphate,
Oh,
so
the N.
pH is phenol. So this one, right?
No,
No,
I meant
the
on
other one, the
N.
next one. And bully.
And beauty? Beauty?
Or in butyllithium. So
Okay, thank you.
that base.
Thank you.
Yeah. And realize my handwriting is atrocious. Okay, so these two pieces in a Wittig reaction are going to be a ketone, which is going to give me this half of my alkene, and this, which is coming from an alkyl halide, reacting with tritone and a base, gives me the ylide, and that's going to give me this half of my reaction, and joining those two carbons are going to be a double bond. So we form an alkene. Okay, so you decide the two pieces. Remember, to form this, I need an SN2 reaction. So the alkyl halide that you start with needs to be methyl primary or at worst secondary. Secondary is not particularly good. This piece, so you need to make a choice. So when you are trying to make an alkene and you're looking at this alkene, you kind of separate this and say which half is going to be coming from the alkyl halide and which half is going to be coming from the ketone, and keep those things in mind when you're trying to build that alkene. Okay, so again, to make the ylide, you start from an alkyl halide, preferably methyl primary, SN2 reaction, add trifenophosphine, this displaces, this gives you this. Now I need to make my nucleophilic carbon, so I'm going to come with a base and butyllithium, which is going to extract this hydrogen and now put a negative charge here. That is my nucleophilic carbon, my ylide. The ylide then goes ahead and attacks my carbonyl, form this betaine intermediate, which then closes, forms this 4-member ring, an oxaphosphatane ring, I don't care, you know the names, but this is very quickly going to break and give me the alkene that I was looking for. Okay. All right. Like I was saying, forming alkenes often resulted in mixtures. So in here, I could have, let's say, added a Grignard. An intermediate product in here would have been the alcohol. Right, after I added the Grignard, I formed this alcohol. And then I do a dehydration reaction. But once I do a dehydration, there's two possibilities. I either remove OH and hydrogen and put my double bond here, or I remove this hydrogen and OH and put a double bond here, right? So there's two elimination products that you form. This one with a double bond here, and this one with a double bond here. If instead I come in with an ylide, this piece is going to end up here, and this piece is going to end up here, and that's going to be the only product, and the major product, as opposed to in here where the least substituted alkene is the minor product. I could end up with 10% of this, whereas in here I end up with over 80% of this as a single isomer. So that is pretty powerful. Okay? All right, so let's do some problem with this. Oh, okay, I'll get to this. I remember that I skipped it. So, if I wanted to make ethyl 2-pentene using a bit. How do I analyze it backwards? How do I do a retrosynthetic analysis here?
You split the alkene in half.
What I'm going to make is a double bond. So now I think backwards, splitting the double bond, right? These 5 carbons are going to join with these 2 carbons. Now, in acidic, one piece is coming from an alkyl halide that's going to form the ylide. The other one is going to come from a ketone or aldehyde. Which one do you think would be better to form the ylide? Yellow or blue?
Blue.
Blue. Because that would mean starting from this primary halide, which is better than a secondary, and eventually adding to this ketone. This primary halide, you would first put your triphenylphosphine, and immediately afterwards add the N-butyllithium. That forms the ylide. Right? I'm going to write it here, but you don't need to write it because I could just write that immediately afterwards the ketone, and that would then give me this product. It's all in the same pot. Make the ylide from the alkyl halide. Once the ylide is formed in that pot, add the ketone, and we got it. I could have made it the other way, but the other way would imply starting from a secondary halide, which is not nearly as good as a primary. So in this case, it should be a clear choice to break it like this. Yeah.
I'm confused where all the carbons highlighted in yellow came from.
Right, ultimately, this is going to go away, this is going to go away, and you're going to end up forming a double bond between these two. Okay. So here's a pre-made ellid on the right, the aldehyde on the left. We're going to form a double bond between these two carbons. What are the two products that form? And the two products that form are cis and trans. Right, we're going to form a double bond here, but you could end up with your two benzene rings like that, or your two benzene rings like that. And needless to say, this is going to be more stable, putting those two large groups as far away from each other as possible. So you don't have control about cis and trans. You have control as to where the double bond is, but whether a double bond is cis or trans, that depends on chances are you're going to end up with both, but in this case, it would be so much more stable to form the trans. That's going to be by far your nature. So women that go through breast cancer, chemo, whatever, once they are in, what's the word?
Remission?
Not recovery, but
Remission.
remission, thank you. Once they're in remission, they give them a drug called tamoxifen. And tamoxifen, so your body or cancer or viruses for that matter are very insidious in that you develop resistance. And what used to work doesn't work anymore because it's found a different mechanism to sort of bypass that. And so tamoxifen is good at kind of any lingering small cells of cancer that are spread in the body. It kind of prevents them from growing, at least for a while. Your body will develop resistance to tamoxifen as well. So they only give it to you for a few years and then they take it away because regardless, it's at that point in time, it's just not doing you any good. But there on your right is tamoxifen. Initially, we started with some pine-type tree that initially found in the islands and then in the western coast of California. And initially they would chop down the trees and sort of from the bark, but then they found that from the needles they could also extract tamoxifen. But eventually it would be nice to synthesize in the lab, right? So one of the big things in here, of course, this is carbon-carbon double bond. And the strategy was to put the two halves together and then join them. So, assuming some enterprising grad student put this already together, what would you need on this side and how would you join them to give you tamoxifen? Okay, show me the steps that you would take to, from this, give you tamoxifen. The only things you have to work with are these ketones, benzene, and inorganic reagents. But those are your sources. Oh, sorry. Any other reagent that you need. But you need to put this together, whatever you need from benzene, or I should say, reagent. What do I need on the right-hand side first to form this double bond? I need
You need a name.
the halide to form the inlet, right? So what initially I'm trying to make is whatever halogen, like this, right? Then I could add trifenophosphine and little lithium from the inlet. So to make this, I need to start from benzene. And then what could I do? To form this. Here I need to make this carbon-carbon bond. How do I make carbon-carbon bonds? Grignards. We're going to let the atoms. It is, but we don't have a bond there. So, let's think Grignard. To make a Grignard, I need to activate this, put a halogen, right? Let's say, do that. What would I add, if I make a Grignard of this, what would I add it to? Usually I add Grignards to carbonyls, aldehydes, ketones. So make the Grignard, add it to this carbonyl, hydrolyze. That would get me the alcohol, right? Can I make this from an alcohol. PBr3 will convert an alcohol to a bromide. So that would be one possibility. I could make this with a Friedel-Crafts acylation, and then I could reduce this, something like that, or whatever strategy you want to build this piece. Once I have that piece, then I'm fine. I'm going to get that piece. Add triphenylphosphine and butyllithium from the Grignard, add that ketone that we saw on top, and that would get me amoxicillin.